Markov chains are an extremely useful object in the study of stochastic systems. You'll find that they actually take a lot of the questions that we looked at in the previous section involving conditional expectation and total probability and things of that sort, and make them really simple to the point that you'll find yourself getting frustrated with the way that we solved them before. So let's take a refresher here. What is a stochastic process? A stochastic process is just a collection of random variables that are indexed by time. And we'll write this as x sub n for n ranging from over the integer 0, 1, 2, and so on and so forth. And the set of all possible values that x sub n can take is called the state space. And here in this section, we're going to assume that that state space is the non-negative integers or a subset of that. So we'll always think about xn as just taking on integer values because that happens to be the most natural way to model a Markov chain. You might remember that we had two examples of stochastic processes. One is where each day you flip a fair coin and x sub n is just the outcome of the coin on that day. That's a pretty boring stochastic process because the outcome on any day is unrelated to anything that preceded it, so it's not very interesting. Maybe a better example would be to let x sub n be all of the heads that you've seen up until that day, so it's a cumulative running total. That would be maybe a little more interesting. So that's a stochastic process. Markov chain is a certain kind of stochastic process with a distinguishing characteristic, which is stated as follows. It's a complicated looking mathematical expression, but actually it implies something very natural. So a Markov chain is a stochastic process such that there exists a matrix with entries ij, so that if xn is equal to I, then the probability that xn plus 1 is equal to j is some fixed value pij. Okay, I don't expect that to sink in. Formally, and I definitely don't expect this thing to sink in. The way you would say this or formally, or the definition of this quote-unquote Markov property is the following. What you're trying to emphasize is that the probability that at the n plus 1th stage, the probability that you take value I, given that you're presently, that you take on value j, given that you're presently in value I. The formal description here, let me erase some stuff here to clarify. If I tell you, if I say I'm currently in state I and I'm looking for the probability that I will eventually land in state j, if I condition also on all of the stuff that preceded me, okay, everything that led up to that point, that probability of going, if I'm in I, of going to j is just some value that depends only on I and j. Okay, so it means that the conditional distribution of the future, given the entire history, depends only on the present state. In other words, it doesn't matter how you got here. So what this really just means is that whatever the probabilities look like going forward into the future, they don't care about all the stuff that led up to that got you where you are. Okay, it's like saying, you always have a blank slate, that none of the events of the past have any influence on what's happening in the forward or happening, in the future. So it sounds like a motivational poster that, don't get bogged down by your past or something like that. That you can start your new future now, or something inspirational like that. So that's what the Markov property means. Now, one big mistake that I find that happens in a lot of textbooks is that they don't use pictures. In my opinion, the best way to think about Markov chains is this picture right here. So what you do is you build a network where you take all of your states, and let's say in this example here we have 5 states in total, which I've numbered 0 to 4. And you think about this stochastic process as jumping from one state to the next. So maybe I start off in state, let's say I start in state 3, and then I move over to state 2, and then you can see a little cycle here, so maybe I go back to state 2, and maybe I go back to state 2 again, and then I go to state 0, and then I go to state 1, and then I go to state 3, and then state 4, and so on and so forth. So you think about sort of jumping along this network, from one step to the next. And so what you'll notice here is in this network, along these links, I have these little numbers. Okay, and those numbers represent probabilities. And you'll notice that if you take any node here and you look at all of the links that are coming out of it, and let's not do 3, let's do one that has, I like number 4 looks a little more interesting. I'll take node number 4, and we'll look at all of the links that are coming out of it, and there are 3 of them, right? There's this one up here with a value of 0.8, and then there's these 2 here which have values 0.1 and 0.1. You'll notice that at any node in this network, if you look at all the outgoing links, those values, those probabilities on them sum to 1. What that reflects is the statement that once you're at a node in the network, you have to go somewhere. And so these various numbers indicate the probabilities of going in that particular direction. Okay, so we'll go back to this one here. Node number 4, you see there's a 0.8 right here attached to this link. This means if I'm presently in node 4, then there's a 0.8 probability that I would go over to node 1. Okay, and now here at node 1, you'll see I've got this little loop here with a 0.1 next to it. That says there's a 0.1 probability. If I'm in state 1, there's a 0.1 probability that I'll go back to state 1 and that I will remain there, right? Then there's also a 0.9 probability that I'll go down here, and so on and so forth. And in my view, this is the best way to think about Markov chains, not through matrices, not through probabilistic statements, but just think about it as if you're jumping along a network and going from one place to the next. Most of the problems from the previous unit can be expressed in such a way, and they become extremely simple as we're about to find. So this is the matrix. This is the Markov matrix associated with that representation I had a moment ago, that network. Right. So what does this mean here? Remember that we had the nodes numbered from 0 to 4. And so let's look for some numbers here. This 0.4 here, what does this mean? This is 0.4 for the 0th row and the first column. And so what that means is if we go back to this picture here, sure enough, you'll see that going from node 0 to node 1 has a 0.4 on it, like that. And equivalently, let's see, from 3 to 4, there is a 0.5. And that reflects that in the third row, again, we're doing 0 indices, so 0, 1, 2, the third row, and the fourth column over here, there's a 0.5. And so you can imagine I could build the entries of this matrix from that network and vice versa. And so you'll notice that the rows in each entry here of this matrix have to sum to 1 because you have to go somewhere. Right, the probabilities are all of, if you're at a particular node of the place where you could land. So they have to sum to 1. A non-zero diagonal element, if you have an element like that, that corresponds to just going back to yourself. And we can see there are 2 non-zero diagonal elements here for the row number 1 and row number 2. And sure enough, if you look back at states 1 and 2, you'll find that they do have self loops. So number 1 has a loop like that, and number 2 has a loop like that. So no surprise there. So this pretty intuitive concept, and it's very, very powerful in terms of what you can accomplish with it. It's used in queuing theory, it's used in artificial intelligence in all sorts of ways. And we'll see some examples of that. It's used in gaming too, actually. A lot of random behavior comes out of systems like this. And so example number 1, very simple one. Weather, in my opinion, is not something that you should really model in a in a Markov setting. I don't think it's actually very useful for that, but it's good for textbook examples just to get a point across. So let's talk about whether it's raining or sunny. Now, let's suppose the chance of rain tomorrow depends only on whether it's raining today. Okay, of course it doesn't. It actually depends on a lot of things, but we'll assume that's the case. And we'll say, okay, if it rains today, then the probability of rain tomorrow is alpha, and if it is sunny today, then the probability of rain tomorrow is beta. So this is a very simple Markov chain, rain and sun. Those are the only two states. And the chain looks like this, right? If it is presently raining, then the probability of rain tomorrow is alpha. That's the probability of going back to yourself like that. And probability is 1 minus alpha of getting sun the next day. And equivalently, if it's sunny today, there's a probability beta of rain tomorrow and 1 minus beta of getting more sun. Okay? So you can represent that with this network. You could equivalently represent it with this matrix over here if you like their equivalent. Okay? That's a Markov chain. Let's do something a little more interesting. Let's do gambling. Not surprisingly, there are a lot of gambling examples in these kinds of stochastic problems. So example number 2, you're playing a simple gambling game where you win $1 with probability P and you lose $1 with probability 1 minus P. So you win or you lose. Obviously, you stop playing if you go broke and have $0. But you also, let's say you stop playing if you make $5. If you end up with $5 in your hand, you're going to say, I'm happy with what I've made, I'm going to leave, and I'm done. So the way you would interpret that is you'd say once you enter state 0 or state 5, you'd never leave because the game is over. And we call those absorbing states. And the way you'd represent that is that you'll notice here that state 0 and state 5 both have a loop like that, but the loop has a probability of 1 attached to it, which just means you always cycle back to that state, which is how you'd represent that. Okay, so how else did this chain look? Well, if I have $2 in my wallet, then there's a P probability that I'll get 3 on the next step, and a 1 minus P probability that I will have $1 on the next step because I win or lose. So this is a pretty it's a pretty simple chain, right? A pretty simple network. You're just moving back and forth like that. And the matrix looks like this thing that you see here. So you've got an off-diagonal entry that's a bunch of 1 minus P's, and then also a diagonal entry that has a bunch of P's like that in it. So that's what's called the gambler's ruin, and we'll study that in more detail later. But that would be another good example of a Markov chain. Right, gambling, I think, is naturally or is sort of instinctively very Markovian. That you know, if you've lost a bunch of games leading up to something, they always teach you in gambling school, if that were a thing, that you know, the outcomes in the future have nothing to do with what happened in the past. Right? There's this gambler's fallacy that says, oh, we haven't seen double sixes in a long time on these dice, and so they're overdue, and so it's more likely to see that. Or people talk about having a hot hand, which again is, you know, just a luck or superstition or whatever. There's no basis in statistics for that, or in probability rather. Another example in weather, but now let's make things a little more interesting. Let's take the weather, but let's say that actually tomorrow's weather doesn't just depend on today's weather, it also depends on yesterday's weather. Okay, so the outcome tomorrow depends on today and what happened yesterday. So then what we'll say is each state will be the weather yesterday plus the weather today. And so then there are 4 possibilities, right? Either it rained yesterday and it rained today, or it rained yesterday and it's sunny today, or it was sunny yesterday and it rained today, or it's sunny and sunny. Okay, and the network, and now we'll say that if it rained today, and then the probability of rain tomorrow is alpha, and if it was sunny, and then the probability of having sun tomorrow will be delta. And then gamma is the probability of going from rain to sun in the ways that you see here. Don't worry too much about the Greek letters here. I actually think what's more interesting is to look at the topology of this network and why it looks the way it does. And so I want to make a diagram here and copy this down to sort of illustrate this. So we've got 4 states here. We've got rain, rain, and we've got rain, sun, and then we've got sun and rain, and then we've got sun and sun. Now this is an example that throws a lot of people off when they see it for the first time. And here's what I want to illustrate. Or the thing that I want to communicate here is, let's say we're in this state here. We're in rain, comma, rain. Okay, so the thing I want to point out is that we want to look at which states you could go to from here. Okay, so certainly you might if you have rain tomorrow as well. So if it's been rain yesterday and now rain today, and we want to know what the state will look like tomorrow, what are the possibilities? Well, it might rain tomorrow, in which case you just stay in the same state, or it might be sunny tomorrow. And if it's sunny tomorrow, then you'd find yourself in this state over here, R, comma, S. Why is that? The reason for this is that if today's weather is rain, in fact, I wish I had drawn this a little bigger. Well, we'll just stick with that. Actually, here, I'll do it over here. Let's do it like this. If do a big R and a big R, if this is yesterday, and that second R is today, and then what are the states that we are going to? The states that we are going to be whatever the value is tomorrow, which could be a rain or a sun. And this is tomorrow. But this state here, what is the yesterday of tomorrow? Well, if I'm tomorrow, then the day that preceded me there would be today. And what is the weather today? Today, this is rain. So the thing I want to point out here is that from the state R to R, you can only go back to R to R, or you can go R to S. But you could not go from R to R to S, right? That couldn't happen. Why couldn't that happen? It can't happen because, again, if it rained yesterday and it rained today, so if it rained yesterday and now it rained today, then what possible state could it look like tomorrow? It can't be that when tomorrow shows up, I'm saying to myself, again, when it's tomorrow and I wake up and it's tomorrow, it's the next day, I can't be saying today it's sunny and yesterday it was sunny. I can't be saying that because I'm presently in a state that it has rained. So the thing I want to just emphasize here is that there are certain connections in this network that are not allowed, right? You can't go RR to SS. You can't go RR to SR because, again, you can't go from RR to an S and then anything, which is why that happens there. What other edges do you not see here? You also don't see SS to RR by the same reasoning. Okay, so that's why this network looks the way it does. That's why not everything is connected to everything else. So the network looks like this, and then the matrix looks like this thing here. There's a problem set problem that deals with weather today and yesterday and the day before that. And so pay very close attention to this example and really try and process why this network looks the way it does. And make sure you understand that third bullet here. That is really critical. Another example would be another kind of game. You might have played this as a child. It's called either Chutes and Ladders or Snakes and Ladders. I think one of them is in Britain and one of them is in the US, if I remember correctly. I don't know which one is which. Chutes and Ladders, I've got this little board here, and you probably remember how this game works. We'll say I start here. Maybe my little player starts there, and then you roll some dice, and let's say I roll a 1, 2, 3. Let's say I roll a 5, and then I would land over here. It's a very simple kids game. And then let's say I roll a 1, 2, 3, 4. Let's say I roll another 5. No. Let's see. This is not a very interesting example. We'll say I roll, I don't know, I land here on my next roll of the dice, and then 1, 2, 3, 4. Okay, now we'll say I roll another 5, and I land here. Okay, now what happens when I land here? There's a ladder, which means I get to ascend that ladder, and then I've jumped ahead, and the goal is just to get to this finish line here. So then I'd land on that ladder there, and I'd be happy about that. What could also happen, though, is you go on these chutes. They're slides that bring you back down, right? So, and what does that do? That looks like, let's say I had landed here before, and then I would go and I'd land on this one, then I'd land on that slide, and that would bring me back down, and now I'd be stuck here, and I'd be going back. Hopefully you remember this game. It's a really simple one, and it's a total Markov chain, right? Because at no point in this process do I care about anything other than what space I am sitting in, right? It doesn't matter what the rolls of the dice were that got me to the position that I'm in. The only thing that matters going forward is which one am I, where am I going to next? So how would you model this as a Markov chain? I'll try and draw this here. What you would do is you'd say, let's assume that I have a normal 6-sided die. And so then from any particular state, you would look at, well, what are the possibilities here? You could say, I'll roll either a 1 or a 2 or a 3 or a 4 or a 5 or a 6. Okay, there's 6 options there. And I didn't need to draw those lines. I can do something much simpler. Here's what I'm going to do. I'm going to say you could roll a 1, 2, 3, 4, 5, or 6. They're each equally likely with a 1/6 probability. And if I roll a 1, what happens? Then I move here and I climb the ladder and I land up here like that. If I roll a 2, then I would land here. 3, I would land here. 4 would be here. A 5 would land me here, and a 6 would land me up here. Right, so you can look at this and say, okay, the probabilities, if I'm presently in this square here, then where could I go? There's a 1/6 probability of going here, 1/6 here, 1/6 here, 2/6 here, because I can get here either by rolling a 5 or a 1 and climbing that ladder, or rolling a 6 would get me there. So you can easily model a Markov chain, you can easily model the game of chutes and ladders as a Markov chain, as this illustrates. Let's do our first non-trivial exercise involving Markov chains, or our first non-trivial sort of investigation, and that is something called the Chapman-Kolmogorov equations. So by now, I hope you recognize that these entries of this matrix, these PIJs, that tells me if I'm currently in state I, that's the probability that the next state I land in is J. Okay, so that tells me the probabilities of where I'm going to land in the very next step. Let's generalize that, and let's say, okay, if I'm in state right now, what's the probability that after the next n moves, I will be in state J, where n is any number we like. It could be 2, it could be 17, right? We'll say, okay, what does my future sort of forecast look like? Some specified number of steps in the future that might be greater than 1. And so we'll write this, to notate this, we'll write it as Pij and then with a superscript n at the top to say I'm interested in going from I to j in exactly n steps. I said exactly n steps. I didn't say up to n steps or anything like that. This is me saying if I'm presently in state I, what is the probability that exactly n steps from now I am sitting in state j? Okay, that's the question. So we'll write it like that, and then it's the probability that that if I'm presently in state I at time k, it's the probability at time n plus k that I will be in j. All right, we'll write that out. Now the Chapman-Kolmogorov equations are a formula that allow me to calculate this. And it works like this. Let's suppose I'm given m and n, which are just 2 integers. The claim is that if I want to know the probability for m plus n, if I want to know, okay, what's the probability, if I'm currently in state I, and I want to know after m plus n steps, what's the probability that I'll be in J? The way you would address this is you'd say, well, what would have to happen? And maybe I'll draw a diagram of this over here. So currently I'm in state I, and this is me, and then here's state J, and this is me in state I at time 0, I guess. And then I want to know what's the probability that I land in state J at time m plus n. And so what you'd say is, well, let's just break this up and let's just think about what has to be true. Let's think about, you're going from state I to some other state. You're state I at time 0 to, some other state in time 1 and so on and so forth. There's all kinds of paths you might take, right? There's a whole lot of ways to get from I to J. But there's a reason that I decided to break things up and look at the state that I'm in time m plus n, which is that we could say, well, let's imagine what are the possibilities for time m. Where will you be at time m? Well, you could be in any of the states probably, right? State 0, state 1, state 2, ... and so on and so forth up to, let's see, state k, and then, all these states here. Okay, so what am I trying to get at? I'm just trying to get at the fact that if I want to know the probability of being in state J at time m plus n, then I could look at all the places I could be at time m, and then the probability of going from state m into that state at time m, and then landing in state J at time m plus n. And now I would apply the law of total probability, which is to say the following. The probability that after m plus n time steps, I go from I to J, what you would do is you would sum over all the states, k, that's this stuff here. Okay, you would sum over every possible intermediate state. You'd say, well, I'd go from in the first m steps, I'd go from I to k, and in the last n steps, I go from k to j, right? That's what's being illustrated here, that in these first m steps, you'd go from I to k to some other node, and then from the last n steps, you'd go from that other node back into j. So I'm just summing over all of the intermediate possibilities that could occur there. Now, if you remember your linear algebra, actually you can say something about this summation. This summation is actually just a matrix product. So in matrix form, that statement that I just wrote looks like this. If I wanted to write a matrix, Pm plus n, where Pm plus n is the matrix of probabilities after m plus n time steps, what I've worked out here is that that's therefore equal to P of m plus times P of n. Right, it's a matrix product, but just by the definition of matrix multiplication here. And what this tells you is that if I take m and n are both equal to 1, then this says that the probabilities after 2 steps just looks like p squared. Okay, and in general, what we have is that P of n, the number of or the probability matrix after n time steps, is just p to the power of n. And so what this tells me is that these probabilities that I want to compute are completely simple. Okay, and this is what the Chapman-Kolmogorov equations say. They tell you that if I take matrix P, the matrix for the Markov matrix, and I could take it to the nth power, all right, just multiply it by itself n times, then if you look at the entries of that, those entries describe the probabilities of landing at these various stages after n steps. So let's do some examples of that. We'll take that weather example before. The weather example that had a matrix that looked like this. This is just the simple weather example where, weather tomorrow just depends on the weather today. And so the matrix looks like this, and I could say, okay, if it's raining today, what's the probability that it's sunny 4 days from now? And what I would do is I would take that matrix, and we've said, let's see, alpha is 0.4, beta is 0.7, which are these, rain to rain probabilities and sun to rain and so forth. And what you do, you take this matrix, just multiply it by itself 4 times, take p to the 4, and you get this thing. And we'd say, okay, what's the probability if it's currently raining? We want the probability that it's sunny 4 days from now, which means that you take this matrix, take it to the 4th power, and then you look at the entry in the first row, because rain comes first and sun comes second in the way we ordered things. So you look at the first row and the second column, which is this one. And that tells me 0.4578. There's a 0.4578 probability that it is sunny 4 days from now. We'll take that gambler's problem too, with your winning probability equal to 0.4. That matrix looks like this. The gambler's problem, if you remember, is the one where you're just gambling at each step, and you lose with probability, or you win with probability p, you lose with probability 1 minus p, and you quit when you're broke or when you've made $5, right? It was that simple chain that's just going to the left and the right. The gambler's problem looks like this, and I can ask the question, if I start with $2, what is the probability that I'm broke by the 5th round or the 20th? And to compute that, we do the following. We say, okay, p is this thing, and so I ask about the 5th round, so I take p to the 5th, and I asked about the 20th round, so I take p to the 20th. And the question was, what's the probability that I am broke by the 5th round if I start with $2? So I start with $2, which means I would look in the 3rd row here, depending on how you index things. So remember, the top row, it means the state 0, you have no money, so that'd be 0, and then 1, and then 2. That's where I started. And the probability that I'm broke is the probability that's in the first column here, the leftmost column. So that's either 0.53 or 0.8, respectively. So 53% chance of being broke in the 5th round, 80% chance of being broke in the 20th round, versus my chances of winning by the 5th round are only 0.11 and 0.19 in the 20th round, respectively. So that's how you would study that. If you wanted to talk about how things are, you expect them to look, in the distant future. Let's talk about unconditional probabilities. In all of the examples we've looked at so far, I've always told you, oh, hey, you start in a certain state, right? I've told you that, okay, given that you presently have $2, or, given that it's raining, what's the probability of being in one of these other states in the future? But let's look at the case where actually the initial state is not even known, right? You might say, oh, you're equally likely to be in any of these states, or there's some particular vector of probabilities associated with these things, and we could try that. So let's suppose that you start off with a vector alpha, where alpha I is the probability that you begin in state I. So of course, alpha is non-negative, and it sums to 1. You could use the total probability here, the law of total probability. You could say, okay, what's the probability that I'll be in state J on the next time step? And you'd say, okay, what's the probability that I'll be in state J next? Well, you'd sum over all the places you could start and apply the law of total probability. So you'd say, okay, if I started in state J, it's the probability of being in state J. I'm sorry, if I started in state I, it's the probability that the next step would be state J, and then multiply that by the probability that I would begin in state I. So these things here, the probability of starting in each of these states would be alpha I, and then these probabilities here are these matrix entries. So it'd actually just be alpha, that vector, times p. So it's another simple matrix multiplication, which makes us happy. A simple example for this one here, we'll again do that weather example because it's a nice little 2x2 matrix. It's pretty simple. But let's suppose the initial state is equally likely. So today we don't know the weather, and we think that it's equally likely to be rainy or sunny. And then I could say, now what is the probability that it will be sunny 4 days from now? So what do? The first thing is I take p and take it to the 4th power, as I did before. And then you multiply that on the left by alpha, by a vector 0.5, 0.5, and I get this vector here. And remember, we had rain was the first column or first row, and then S was the second column or the second row. And so I want to know the probability of being sunny 4 days from now. That would be this thing here, 0.4618. And we'll do that gambling problem again. So let's suppose that, so before in the previous example, I told you you have $2 and you start gambling with this. Now let's suppose that the amount of money that you start with is uniformly distributed from 0 to 5. So the amount of money in my wallet is random, as often seems to be the case. So we'll say it's uniformly distributed from 0 to 5, and so I have a 1/6 entry for each of these alpha i's, because 1 and 6, because there's 6 possible states, 0 to 5. And then I can ask the same question: what is the probability that I'm broke by the 5th round? So once again, you take this matrix product, p to the 5, and multiply that on the left by alpha, which is just a vector of all 1/6s everywhere. And you get this thing. And what you should notice is that the biggest terms are either in the 0 or in the 5 section. They're at the endpoints, right? And what that tells you is that you're likely to have ended the game by this point, by the 5th round, right? The large numbers here tell you the game is probably over by round number 5. You might have won, you might have lost. But in any event, you have these very small probabilities within the middle. It's very unlikely that the game will still be going on. And that's what's reflected there in that vector. Some terminology here, which very intuitive in my opinion. Don't worry too much about memorizing all of this. It'll come in pretty naturally. We'd say a state J is accessible from state I if it's possible to be in I and then eventually land in J at some point in the future, right? It means if I were to draw that network with the nodes and the links in it, it means there is some way of getting from I to J by some sequence of links. If J is accessible from I and I is accessible from J, then we'd write that like this, a double arrow between I and J, and we'd say those states are communicating. Like you can go back and forth between them all you want. By definition, of course, every state communicates with itself. Also, if I and J can communicate, and J and K communicate, then certainly I and K communicate. These are all just kind of natural statements about connectivity and networks. I'm not saying anything profound. You can divide the state space into classes based on which states communicate with which other states. If a Markov chain consists of one class, we'd say it is irreducible. And a class of states is closed if it is not possible to leave that class. Like if once you're stuck in a situation, you can never leave that. You're in some cycle that goes on forever. So we'll see examples of that. An absorbing state is the thing I showed before in that gambler's problem, where for example, you go broke and then the chain is over because the game has finished. That would be an example of a closed state, but it's a closed class, or it's a closed class with just one element, right? You get 0 and you never have anything other than 0, and so you're stuck. You can think about things like a chessboard. If you're a bishop, right, you can only move on one color. You move diagonally on a chessboard, so you can only move on the white squares or on the black squares. So for a bishop, they're closed. The chessboard is broken into two closed classes. For each state I, let fi be the probability that if I start in that I will ever come back. If fi is 1, then that state is recurrent. And if it's smaller, if less than 1, then we say that state is transient. So we'd say a state is recurrent if you know that you are always going to visit this state infinitely many times if you run this chain forever. Whereas if that probability is less than 1, then once you leave that state, you might never come back to it, in which case we'd say transient. Again, these all make sense much better with pictures versus with prose, and so let me show an example of this. This would be an example of a chain that is not irreducible. Its communicating states are 0, 1, and 2, and then 3 and 4. All right, so 3 can get to 4, and 4 can get to 3. But then you can see here, 1 and 3, for example, do not communicate, because if I'm in state 1, I can get to state 3, but then I can never get back into this left group over here. I can never get back to state 1. So 3 and 1 do not communicate, and 3 and 0 and 3 and 2 do not communicate either. Right? These two groups here that I've identified do not communicate with one another. This class 3 and 4, this is a closed class over here because you're just going to go and loop back and forth between 3 and 4 forever. So that class is closed. This class on the left is not, because you could go from 0 to 2, if 1 to 2 is 0. Sorry, I didn't loop back here like that, and then go back to 2. You could move around here, but eventually you might move out and land in this other set here. So the set on the left is not closed, but 3 and 4 are. So it's intuitive, and it's not hard to prove that if two states communicate, then if I is recurrent, then so is J, and that's just sort of an aside here. So we would also say that states 0, 1, and 2, this class over here on the left, these over here, you would say they are transient, because there is a probability that once I'm in that state, I might never come back to it, because that might be the time that I jump into this group over here on the right. All right, so that's just some terminology there. Hitting probabilities. Okay, hitting probabilities are telling me what are the probability that I might ever reach a certain set. Okay, let's begin with a really simple example. So if I identify a subset A, a subset of nodes, which could be whatever I want it to be, any subset of nodes, and I is an element of the state space, the hitting probability from I to A is the probability of ever landing in the set A if I start from I. Okay, so what do I mean by this? If A is 0 and 2, so I say I am interested in the set 0 and 2. I'm interested in, oh, that's not 2, that's number 3. If I'm interested in this set down here, 0 and 2, and then what I'm going to ask is, I want to know from all these other states, 1, 3, and 4, I'd like to know what's the probability that I will ever land in state 0 or state 2. Okay, so what is true? Well, if I'm in state 0, then of course the probability is 1. Right? If I'm in state 0, then the probability that I'll ever land in state 0 or 2 is of course 1, because you're there. Okay, equivalently for state 2, the probability is also 1. How about if I'm in state 1? What's the probability that I'll ever land at any point in the future in state 1, in state 0 or state 2? Well, look at state 1 here. State 1 only has two choices. You either move off to the left and you land in state 0 with probability 0.3, or you move off to the right, and once you do that, you enter this closed class of 3 and 4, and at that point, you're never going to visit state 0 or state 2. So in state 1, we'd say, actually, there's a 0.3 probability of this ever happening, because you either go to the left on that next step, at which point you land in state 0, or there's a 0.7 probability that you never visit them again because you've moved off to the right. For states 3 and 4, because they're a closed class, it's easy to see that you're never going to go from states 3 and 4 to state 0 and 2. Okay, so this thing here, this vector, is called the vector of hitting probabilities associated with the subset 0 and 2. So we were able to work that out in this example because it happened to be really nicely structured, but let's try and work out a more general approach and see how this works. Let's try this example. We'll set A now to just be a single state 3. I want to know what's the probability that I'm ever going to land in state 3. And so what is true about this? So obviously h3 is equal to 1. Sorry, I should describe my notation here. I'm going to say h sub I, I'll say it like this, h sub I, I'll write it down, h sub I is equal to the probability that I ever land in state A, that I ever land in state, sorry, not state, land in the set A if I am presently in state I. Okay, so that's what that means. It means if h sub I is like if I'm currently in state I, it's the probability that I will at some point in the future land in state in the state A, or in the set A. Sorry. So okay, so I'll say A is just this thing here, number 3 on the right, and we'll compute these hitting probabilities. So h3 is equal to 1 because if I'm in state 3, then I'm there, so I've already accomplished my goal. And let's look at h1. So what is true about h1? So h1, we can say what's the probability of ever, if I'm in state 1, what's the probability that eventually in the future I at some point land in state 3? Well, you'd say there's a 0.5 probability that I go to state 0, which is absorbing. And once I do that, I'm never going to escape it. So there's a 0.5 probability that this does not happen. And so what is the only thing that's left? Well, the other option is there's a 0.5 probability that I go to state 2. Okay, and so therefore I'd say, well, h1 is 0.5 times h2. Because what needs to happen, there's a 0.5 probability that I'd go to state 2, and then I'd say, hey, look, now I'm in state 2, so what's the probability that I land in state 3 at some time in the future? Well, that's h2 by definition. And so what is true about h2? Well, h2, you would look at this and you'd say, what's going to happen if I'm in state 2? Well, there's a 0.5 probability that I just go into state 3 and I accomplish my goal. So there's a 0.5 probability there of taking care of this. And then the other bit is there's a 0.5 probability of going over to state 1, at which point I'm in state 1, and I have to work with that. So now I've got 2 equations and 2 unknowns, right? h1 equals 0.5 h2, and h2 equals 0.5 h1 plus 0.5. So I could solve for those, and if I did that, I'd get this system here. I'd get, obviously, h0 is 0, because if I'm in state 0, I'm never going to land in state 3. Whereas if I'm in state 1, then there's a 1/3 probability of ever landing in state 3, a 2/3 probability of ever landing in state 3 if I'm in state 2, and then obviously a 1 over here. So that's another example that we were able to solve by reasoning this out. And let's see how general we can make this. We'll do another example, and this time I won't even draw the chain. I'll just give you this matrix, and we'll recover these equations just looking at these entries. We'll ask the hitting probabilities of ever reaching the second state. And you'll notice that in this example here, I put my indices from 1 to 5 instead of 0 to 4. So please bear that in mind when you look at this example. So we're asking the probabilities of ever reaching the second state. So obviously h2 is 1, because again, if I'm in the second state, then I've accomplished my goal. How about h1? If I'm in h1, then where could I go? I could go back to h1, or I could go, sorry, if I'm in state 1, I could either go to state 1 again, that's this 0.3, or there's a 0.7 probability that I will land in state 3. Okay, and so I'd say h1 is equal to 0.3 h1 plus 0.7 h3. I would say if I'm in state 2, we already covered that one. State 3, there's a 0.5 probability of going to state 1, and then a 0.5 probability of going to state 3. If I'm in state 4, then there's a 0.2 probability of going to state 1, a 0.5 probability of going to state 4, and a 0.3 probability of going to state 5, and therefore h4 is equal to 0.2 h1 plus 0.5 h4 plus 0.3 h5. Okay, so you see what I'm doing here? I'm just writing out these hitting probabilities. You just take the sum of the, take these matrix entries here as coefficients of these h's, and you have a system of equations here that looks like that. Okay, so in general, the system of equations just looks like basically follow that pattern that I've just written. You'd write that for each I, you'd say hi is equal to it's either 1 if that state is already in the target set that you're interested in, and then otherwise you just sum over all the states in the chain j of pij times hj. Okay, so all I'm writing here is the formal expression for the pattern that is sort of implied in this example here. Okay, now the previous system, it turns out, was actually underdetermined. These systems tend to have a singular, they're generally a singular if you just write them out as written from the matrix, which isn't actually a problem. But the solution would take this form here. So you can see there's a degree of freedom here that you can set H4 to be anything you'd like. But you can't, of course, set H4 to be anything you'd like because H4 can't be negative, for example. And certainly all of these probabilities they can't be greater than 1. And so the way you resolve that, we won't bother to prove this because it's kind of a messy thing. The way we resolve this is the following, through the following theorem, which is that the vector of hitting probabilities is the minimal non-negative solution to that system that I just wrote before. And when I say minimal non-negative, I mean that you take those entries that are free, the entries that are not specified, and you should make them as small as possible. So in this system that I had before, you saw we had 1 degree of freedom, which I put into H4. And this says make H4 as small as you can, but keep non-negativity of all of these entries here. And it turns out the value that you would want to do to choose that would be setting H4 to be 3/5. So you fix H4 to be 3/5, and your hitting probabilities look like that. So there's a 3/5 for H4, and then some 1s and some 0s in other places. So those are hitting probabilities. Now let's use this to study that gambling problem. Okay, this is something called the gambler's ruin, as I mentioned before, where you're gambling and you win each round with probability P and you lose with probability Q, which is 1 minus P. And we're going to look at this kind of problem and say, well, what is the eventual probability that you end up winning and leaving the problem, or leaving the game, versus going broke? Right? Let's ask, what are the probability that eventually you win or that eventually you lose? So obviously H0 is 0 and Hn is equal to 1. So n will be the amount that you are willing to leave with. And in this diagram here, n is equal to 5. But we're going to do this more generally. So here these h's will be the hitting probabilities associated with the rightmost state, which is the good state of winning, the state that you like. So Hn is equal to 1, H0 is equal to 0. And so we're going to ask, what is the formula for these general HIs? Right? If I want to come up with $500 and I currently have $400 in my wallet, what is the probability that I'll eventually win as opposed to eventually lose? So let's work those out. So what do those equations look like? We'll draw a diagram here, but I think you can probably work this out. What's going to happen? I've got here's state I. This is me with $I in my wallet like that. And then where could I go? I could go to state I plus 1, or I could go to state I minus 1. And the probability of going to I plus 1 is P. And then the probability of going to I minus 1 is Q, which is, of course, 1 minus P. And therefore, I would write that H sub I is equal to P times H of I plus 1 plus Q times H of I minus 1. Okay, that's the system that comes from that, and you do this for every I, except for I guess h naught and hn, where you've got a 0 and a 1 there. Okay, so I've got a system that looks like this, and since p plus q is equal to 1, I can take these hi's and write that this hi is equal to phi plus qhi, because again p plus q is equal to 1. Or I could just shuffle this again, just doing boring old algebra. Hi plus 1 minus hi is equal to q on p times this difference here. It's okay to let your eyes glaze over a bit. I'm just doing some kind of tedious algebra that you don't really need to remember. So let's try building these terms up one by one. So I know h naught is equal to 1. And so therefore, I can build the other terms off of that. If you look at the, because I had things expressed in this recursive fashion over here. Excuse me. And so we could do that. We could work out that okay, h2 minus h1 is q on p times h1. h3 minus h2 is q on p squared times h1. h4 minus h3 is q on p cubed times h1, and so on and so forth. And so if I add the first I minus 1 of these things together, I get hi is equal to h1 times the sum of all these powers of q on p. So now what I have is I've kind of reduced everything in terms of the initial value h1 in terms of all these other things. And so what is true now? So now you do a power series. You'll use an observation, which is that for any x that is not equal to 1, you have a sum of the powers. The sum of the first n minus 1 powers of x is equal to this expression over here. And I'm going to prove multiplies both sides by 1 minus x. And therefore, provided that q is not equal to p, what this does, this gives us an analytic expression for this summation. And so if I plug in the case x equals p on q, which is what's popping up over here, the thing that you find is that h sub I is equal to this thing here, so 1 minus q on p to the I on 1 minus q on p times h1. And then I'd say that since h sub n is equal to 1, remember n is me winning and leaving the game, so then I've accomplished my goal. So h sub n is equal to 1, which therefore tells me that if I plug this in here, capital N in this numerator, it says that if I plug this thing in here with an n substituted for I, then that would have to be equal to 1, and that lets me solve for h1, which is equal to this expression. So what have I done with all this algebra? What I now have is I have a closed form expression for the probability of winning given any of these states. And it says h sub I is equal to 1 minus q on p to the I divided by 1 minus q on p to the power of n. Now, when q is equal to p, in other words, when they're both equal to 1/2, you can follow through the same kind of reasoning and just find that in that case, h sub I is equal to I on n. So now that this lets us reason about gambling games in a pretty clean way, right? I can say if I'm trying to get $500 and I've currently got 400, I can use this closed form expression to work out the probability that I will achieve my goal as opposed to losing and going broke. So what do we notice about this? When q is less than p, okay, when you're more likely to win than to lose, then let's ask what happens as n goes to infinity. Okay, so what am I saying? I'm saying it's a game that's favorable to me. It's a game where I'm more likely to win than to lose, but the standards I'm setting for myself are very, very high, right? I'm saying n goes to infinity, so I want to win a lot of money. So n goes to infinity, and you fix I, but h of I is equal to this thing, this quantity here. It approaches 1 minus q on p to the I, which is strictly positive. Okay, because I assume q is less than p. Okay, so then as n goes to infinity, I still have this positive probability of ever actually achieving my goal. But if q is greater than or equal to p, then when n goes to infinity, this quantity goes to 0, which is not surprising, right? If I'm setting loftier and loftier ambitions for how much money I want to make, but the game is actually unfavorable to me, then I'm just making things harder and harder for myself, and I'm eventually the probability will be 0. So the second statement is obvious, because eventually you'll lose if you're demanding that you earn lots and lots of money. That's why casinos exist. But the first statement is a little weird, right? The first statement actually says that there's a positive probability that you'll just keep making money forever, right? If I have a game that's actually favorable to me, this says that there's a positive probability that if I just keep playing until the end of the universe, that I can play the game forever and never go broke, which is kind of unsettling to a lot of people, because you're talking about an infinitely long time span over which you somehow continue making money forever and never go broke, which is not something you usually expect to happen, right? Strange things happen at infinity. You could apply this to, we had an example before that involved players A and B that were playing a game, and you had to win by 2. We did that in conditional expectation previous lecture, and now we'll do it winning by 3 for no particular reason. And it looks like this. You've got A and B. They're playing a series of games, and A has a probability P of winning each game, and the overall winner is the first person who wins, who is ahead by 3. Okay, and we're going to ask, what is the probability that A is the overall winner? Well, this is really just a gambler's ruin chain, isn't it? Because we could re-index things, and we could say, okay, the gambler's ruin chain went from 0 to n, but now let's just write a chain out that indicates, how many turns ahead A is. So state 0 represents where they both have, they're tied, and then a 1 would be A is ahead by 1. A 2 would be A is ahead by 2, and 3 would be, of course, A is ahead by 3 and wins. And ditto for -1, -2, and -3, which I've written over there to the left. This is, B is ahead by 1, B is ahead by 2, and then B is ahead by 3, like that. Okay, so you look at this and you can say, well, actually, this looks just like a gambler's ruin chain. The only distinction here is that instead of using numbers 0 to n, I've used numbers, in this case, -3 to 3, because you have to win by 3. But I think it's pretty clear that this chain fully captures the process that is described here. So it's a simple Markov chain. It's actually a gambler's ruin problem, right, with some different indices in it. But again, I've just written those equations out here. You solve them, you plug in that formula for the gambler's ruin, and you'd say, well, we want to look at H0, right, because we're starting off with the score being even, so we want to look at this thing in the middle. And H0 turns out to be this expression here. Okay, you could calculate these easily and write them out, but we won't bother doing that because there's not much to be gained from it. Okay, so that's what that probability is. And I want to notice here, right, I'm not doing a lot of contrived sort of conditioning arguments, right? Everything sort of follows from this chain. I'm just using this expression over and over again, which I think visually helps a lot in terms of formulating and solving these things. We did this example before too. It's the world's most boring game. You have 2 players that are just taking turns flipping a coin, and the winner is the first person who gets heads. And so the coin is weighted funny. It's got a probability P of showing heads. And we'll say, okay, what's the probability that the first player, A, wins this game? Now, you just saw this example not in the context of Markov chains, but now you're going to see how easy it becomes when you allow yourself that luxury. It's a very simple Markov chain, and we'll label it as follows. We'll say W means that A wins, L means that A loses, and then A and B just indicate who's holding the coin, right? So this state here means A has the coin. There's a probability P that A is going to win, and a probability 1 minus P that the coin gets handed off to B, who then takes their turn as well. This is not a gambler's ruin chain, as you'll notice, because you have an arrow that goes 1 minus p over here to the right, and then an arrow that goes p over here. So the probabilities of going to the left are not consistently always p or 1 minus p. They're not symmetric in the way that we had before. So this is not a gambler's ruin chain, but you can absolutely just compute these hitting probabilities. And they look like this. It's a very simple system, right? We're asking what's the probability that A is going to win. In fact, I'll write out the system here, even though I think you probably can follow along pretty well. But I'll go ahead and do that. So we'd say the probability that A wins, we'll write that as H. And so H sub W, that's the probability that A wins if you're presently in state W, which of course is 1 because A is just 1. H sub A is going to be what? What can you do from state A? Well, you can either go to state W or like that. You either go to state W or you can go to state B. And the probabilities of those happening are P and 1 minus P respectively. So HA would be P times HW. And of course we know HW is 1, but we'll act like we didn't know that and just write out the expression as generally as we can. Plus 1 minus P times H sub B. And then H sub B is going to be, what H sub B is going to be, you either have a 1 minus P and you go back into state A, or there's a probability P of going into state L. L, of course, stands for losing, so we happen to know that HL is equal to 0. But again, we'll act as if we'll use it freely in these other expressions too. Okay, so now I've got these equations here, and if I work those out, you'll find these expressions here. H sub A is 1 on 2 minus P. H sub B is 1 minus P divided by 2 minus P. So that's how that works. Another example here, we'll say I'm sitting here and I'm rolling a die, and I'm following the following set of rules. I'm tossing this die and I'm writing down the number, and I keep adding up these numbers together. So I'm keeping a running total of all the numbers that I've rolled, and I stop as soon as the sum is greater than or equal to, or is greater than 10. Sorry, strictly greater than 10. I stop when that happens, and then I want to know the probability that the game finishes, and the total sum that I have is equal to 13. So I'll do an example here. I'll roll the dice once, and I happen to show a 6. And I'll roll the dice again. Now I have a 3, so 6 plus 3, which gives me a total of 9. And I'll roll it again, and now I saw a 2, which gives me 11. So now I would stop the game because the sum has exceeded 10, and I ended up with 11. Right? So what are the possible outcomes here? You're going to stop on 11 is actually the smallest number you could stop at, which is what I happened to stop on. Or you could stop at 11, 12, 13, 14. Let's see, 11, 12, 13, 14, 15, or 16. I guess is the highest number that you could stop at. And so the question is, what is the probability that when you finish this game, you finish with a sum of 13? Okay, of all the numbers you could end with, 11 to 16, what's the probability that you end with a sum equal to 13? Okay, so let's model this as a Markov chain and see what that should look like. Let's draw the picture here. So let's say we start on an initial state of 0, and I'll just try drawing this chain as nicely as I can. So you start in state 0, and let's just look at all the states that you could land in. You could go, well, I'll write everything here. There's state, well, no, we'll do it like this. So from state 0, you could roll a 1, or you could roll a 2, or you could roll a 3, or a 4, or a 5, or a 6. Okay, like that. And I'll draw more parts of this chain here. I'll do 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh, I can't quite fit it in, too bad. But it's okay. It's a really ugly drawing anyway. And then you'd say, okay, for example, let's suppose I'm in state. I won't draw the whole chain. It's just going to get really ugly. But let's say I'm in state 5. Right? If I'm in state 5, what are the possible things that could happen? I could go to state 6 because if I've totaled up to 5, then I either roll a 1 through a 6, and so I'll either land in 6, 7, 8, 9, 10, or 11. Right? Those are my possibilities, and and so on and so forth. Right? That's pretty clear, I think. Basically, you take for any state that you're in, you look at that state plus 1 up to that state plus 6, and you have an equal likelihood of going to any of those, and that's what I've written here. Okay, but once you exceed 10, the game stops, right? And so that means that states 11, 12, 13, 14, 15, and 16 all just have a self-transition like that, right? They're absorbing, and they just go back to where they should be, or they go back and they stay in that state. Okay, so I've written out my transition probabilities. I could draw this in a great big matrix if I wanted. And so to compute these hitting probabilities, you would just solve the resulting linear system, which I've written up here. And when you do that, you find H0 is equal to 0.1819. Okay, so there's about an 18% probability that the final number that you land on is 13. So the smallest entry is H6, which is 0.1421, and the largest entry is H7, which is 0.2647. And so actually, let's draw this. So remember, the question that we're interested in is, what is the probability that you eventually land, or that you land on state 13, right? That's the one that we're interested in. And so, okay, how could you land on state 13? I want to make sure I do this in a way that actually fits into my, into my drawing pad here. 11, 10, let's see, 9, 8, 7, 6, 9, 8, 7, 6. Yeah, I think I can do this. 8, 7, and 6, like that. Okay, and so I've got this diagram here. And I guess the point that I want to emphasize is just the following. If I'm in state 7, which is the state that is most likely to land in state 13 eventually, if I roll a 6, I would land in 13. A 5 or a 4 would not be useful to me. But then if I roll a 1 or a 2 or a 3, I've still got the chance open of landing on 13 on the next roll. Right, so there's a way that I could do that. However, if I'm in state 6, then rolling a 6 would bring me only over here to 12, and so the options there are more restricted for my movement in terms of that. Hand wavy argument. Okay, don't worry about that. I'm just trying to make some kind of qualitative observations here.